All right, good day, everyone. Now, this is the Unit 2 aspect of cave physics. So, to begin this lesson, we want to look at electrical quantities, right? And throughout the duration of this course or this lesson, we will look at the following objectives. So, we want to use the equation Q is equal to I T, where Q stands for charge, I stands for current, and T stands for time. Now, if we can recall in CSEC, we would remember that current is equal to the rate of flow of charge, which in the formula sense it looks like this. Q divided by T will give us the current. So in order for me, if I want to find my charge, then I would have to simply manipulate this. All right. Now we're going to look at charge that can be recognized as such, where N refers to the number of charge, and E refers to the charge of an electron. All right. We want to be able to can define coulombs. Now, as we should know that the units for charge is coulombs, and because of that, we want to know what it is. We also want to become more familiar with the definition for potential difference, volts. The syllabus wants us to use the following equation that says V, which stands for potential difference, is equal to W over Q. We'll look at that in short order. We also want to use this equation, our Ohm's law equation, that says V is equal to IR to solve some questions. We also going to introduce to you guys a power equation, right? And this power equation can be written in three different ways, right? So one is written in respect to I, whereas the others can be written in regards to finding the resistance and all of that. Now, on the screen here is a table that consists of some components, right? So be familiar with these components, where as you can see, this is what we would use to represent a cell. This is the one that we'll use to represent a battery. All right. So be aware of those symbols. Resistors. You have a variable resistor. That's the one with the arrow going through it, right? So all of these we will more than likely come across, right? But more importantly, we'll mainly come across resistors, voltmeters, possibly lamp, ammeter, and a cell for the most part, and maybe a few switches, so to speak. So we'll come across that. Now, let's get into the meat of the matter. All right. So electric charge, which is denoted by Q, uh, really is what you know. So charge in itself is a particle, right? And we have to understand that whenever we're dealing with circuits, it is the charge that allows things to work, so to speak. It's the charge that allows it is the electrons. So by the way, charges can be positive or negative. So if I say electrons, I'm speaking of the negative aspects of the charge. So those are what we use to run our components. Whenever you plug in a device, it is charge that is flowing through that device so that it lights up and all of that. Now we have to understand that in order for electrical energy to be transferred around a circuit, there has to be some amount of movement of charge, right? Now, if we look at a metallic conductor such as copper, this material would have a lot of free electrons, or we refer to those as charge carriers, right? Now, those charge carriers has a specific unit, and as we made mention earlier, Ron, is that the unit for that is coulombs. The symbol, as you can see on the screen, is a capital C, and it's right here. Now, coulombs can be defined as this. It says on the screen that it is the amount of charge that passes a point in a wire in 1 second where the current is 1 amp. So 1 coulomb is that amount of charge that passes through a wire in 1 second when the current is 1 amp. All right, so that's the definition that you will have to know, because the syllabus requires for us to know that. Now when it comes on to an electron, we said that an electron is a charge, and we also said that it's negative. That charge has a value in terms of coulombs, right? So based on my screen here, we realize that any electron will always have this amount of charge, which is negative 1.6 times 10 to the minus 9 coulombs. All right. Yes. So that's a thing that we'll generally have to know right across the board whenever we are. It's a constant, right? And it's something that you can always remember right off the bat. That charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. We will definitely use that a lot in this aspect of the course. So we know that it is negatively charged, and it says therefore the actual direction of the charge flow in a circuit is from the negative terminal to the cell of the cell, rather, to the positive terminal. What this is telling us is that in physics so far we have come up with this notion that uh, charge flows from the positive terminal to the negative, right? We have hold on to this concept quite some time, and for that reason we call it the conventional current, right? So it is something that is still accepted, okay guys, but in reality, what is happening? So this is for the conventional current. That's how it flows. The reason behind this was that at the time when they were investigating electricity and all of that, they did not come up with, the electrons and so forth. So they just decided that, for argument's sake, let's just find out their direction, and we'll say from positive to negative. All right, because positive, I guess, probably sound much better to them. But after realizing no and doing their other investigations, they realized that, that's not the case. What's the case is that we have a circuit here with a battery. This is the positive terminal. This is the negative terminal. The reality is that the current, because the electrons are the charge carriers, right? They are the one that are going to are going to basically allow the current to flow. And because they're negative, we'd expect that they would move from the negative terminal to the positive, right? So this is the actual thing that happens whenever a circuit is designed. The charge, negative charge, they flow around the circuit from the negative terminal of the cell to the positive side. But we have adapted this one here, and it's one that we still use up to this date, right? So still use up to this day. All right. So as we said, this is the conventional current. Now, when we talk about current, we said it earlier on that current is equal to the rate of flow of electrical charge, and this is how we would write our equation. Whenever we talk about rate, we're talking about time, right? And of course, we should know that the the units for current is measured in amps, where the symbol for the unit is a capital A. All right. Now the device here that we use, I think it's probably written somewhere in the slide here, but the device that we use to measure current is what we call an ammeter, right? And that symbol for an ammeter is just a circle with a, a capital A written inside of it, right? Good. Now, another component or quantity that we will come across in this aspect of the course. So we have gone through charge so far, so we know what is a charge, so to speak. We know that, uh, we know the charge of an electron. We know that we now know that the charge in a circuit actually flows from negative to positive, right? Now we want to look at another thing, what we call, we know about current already, which is the rate of flow of charge. All right. Now let's look at what we call potential difference. So when electrons flow through, circuit components such as a lamp, right? The electrical energy given to the electrons by the power supply is converted to other forms. So what we're saying is here is that whenever we have a circuit set up, right, electrons are going to flow through the components. Now we need to understand that there has to be somewhere where the energy is coming from. That energy that is that the cell that the not the cell the energy that the electron receive comes from the power supply, right? And we have to understand that that electrical energy, right, from time to time is going to be converted into different forms. And we see where if the charges were being flown through a lamp, it would convert from electrical energy into heat energy and light. So when you plug in a lamp, you get heat from the lamp and you also get light. So we see where the energy has dissipate, or we see the two other forms of energy that has been converted, right? Now, in order for that to happen, right, there is some amount of work that needs to be done in order for the heat to be in order for the electrical energy to be converted into the heat energy or the light energy. Let's see what this is saying. The energy transferred to other forms per coulomb of charge that flows through a circuit component is equal to the potential difference. So the energy which comes from the power supply, right, that is transferred to other forms per coulomb of charge is what we call the potential difference. So every component that is in a circuit. So let's imagine that this is my lamp, right? And I have a resistor in the circuit. These are what we call components. Here's my power supply. is going to flow through these wires here until it reaches this component. Now, at this component this component needs to convert the electrical energy into that energy per coulomb that is uh, flowing at this point is what we refer to as the potential difference. Now, one of the reasons why we call it potential difference is because at this point, this is the positive potential of my 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 bulb, and this is the negative uh, side. And between here is going to be a different charge. So finding the difference between these two, in a sense, gives you what we call a potential difference. All right. So as we said, so the amount of energy that is converted per coulomb gives you the potential difference between the terminals. So this is one terminal here, and this is another terminal. Now let's look at this. It says potential difference has the same units as electromotive force and is measured in volts. So the unit here, so after we finding out how much energy it will take to convert uh, that amount of charge, right, into light energy, then we we come up with a unit what we call volts, right? So the units here is going to be volts, and we also said that electromotive force is and potential difference has carry the same unit, but they're a little bit different, and we'll look at it right now. But let's just define what a volt. By the way, before we go there, so this right here is that equation that we would use to find the volt. Now we know that the symbol for volt is V, and we're saying that the energy transferred from electrical to other form, right, divided by the charge gives us the volt. Or we can say the work done, right, by the charge. Let me see if I can say that again. So in order for the light to come on, you understand, the charge that is flowing needs to do some amount of work. So that work, which is measured in joules, divided by the actual charge that is flowing through the component, will give us the volt. So in other words, a volt is in terms of these units is equal to joules per coulomb. All right. So we have seen that so far. So let's look at what this is saying in terms of volt. So he said a volt is the potential difference between 2 points such that the energy transferred from electrical to another to other forms is 1 joule per coulomb. So we see where this is an another unit that we could write. So in terms of if we see this, if we see joules per coulombs in any equation, we know that is talking about volts. All right. Now, as we said, electromotive force and potential difference carry the same units. Now, when it comes down to electromotive force, this is what it is saying: the energy given to each charge or to each coulomb of charge that flows around the circuit is determined by the electromotive force of the cell. So remember now that a battery, or a cell rather, has energy stored inside of it. When before remember now, before anything can happen to the light bulb, right? It would need a source of energy to allow the electrons to move around the circuit. So that is the force that we're talking about. That electromotive force is that energy that comes from the cell, from the battery, or the cell in this case, that would propel these negative charge to move around the circuit so that the light bulb can now lit up and all of that, right? So that is what it is saying, that the energy given to each coulomb of charge that flows around the circuit is determined by the electromotive force of the cell. So what this can also tell us is that if I have a low voltage, if my voltage, not my voltage, if my power supply has a rating of 2 volts, what this is telling me now is that this is the amount of energy that I can produce in a given time to allow my electrons to move around the circuit. So this can also point out to us to say that the higher the value of the power supply, it's much it would give the cells more energy, so to speak. Not the cells, the electrons rather. It will give the electrons more energy to be able to can move around the circuit. Now let's see if we can look at a simple problem here. What is it saying? It says electrons in a particular television that are accelerated by a potential difference of 20. So we know that potential difference. Another way we can write potential difference is by saying PD, right, is equal to 20 kilovolts between a filament lamp and the screen. The charge of an electron is this, right? So we know that the charge, so electron is equal to negative 1.6 times 10 to the minus 19 coulombs. They want us to find, or they want us to calculate the gain in kinetic energy of each charge. So we know let's look at it again. Electrons in a particular television are accelerated by a potential difference of this between a filament lamp and the screen. The charge filament and the screen. Alright, so we know that our power supply has this amount of potential difference. No, not the power supply. The between the filament and the screen, this is the amount of potential difference that is required to accelerate the electrons. So if I want to find out how much energy the electrons have, I would have to pull up this equation that says potential difference is equal to work done divided by the charge, Q. Now the work done is the same thing as the kinetic energy, because the electrons are moving, right? So that is what this energy is at this moment, or this is the work that is being done. And we know the charge is an electron, which is 1.6 times 10 to the minus 19 coulombs. So let's see. So that work that would require the electrons. Oh, so yeah, we don't know the work, so we have to just go ahead and transpose to finding work. So let's see. So I would need to bring this on the side of the equation. No, not there. Let me rewrite this. So PD times E, which is the charge of an electron, 1.6 times 10 to the minus 19, is equal to the kinetic energy. Yes, and we know the PD is 20 times 10 to the 10 volts times the 1.6 times 10 to the minus 19 will give us the kinetic energy of a single electron. By working that in your calculators, we should get a kinetic energy of 3.2 times 10 to the minus 15, and the unit would be joules. All right. Now, so that would cover that, where it speaks on all right. So other points that we need to make note of. Note that whenever we're measuring current in any circuit, the ammeter must be connected in series with the component that you want to measure the current across. Right? Now, the reason why we can go ahead and put an ammeter in series is because of how it is designed. It is designed to have a very low resistance, and sooner than later we'll talk about resistance, right? So just note that an ammeter must always have low resistance, and it must be in series with whatsoever component that you're measuring the current uh, through. You understand? So this potential difference on the on the other hand, it, you you generally use a voltmeter to measure the voltage, and the way how you have to set it up is that your voltmeter must be in parallel with the component that you're measuring the voltage of. Here is a diagram below that kind of highlights it a little bit. So if I wanted to measure the current here, it would be safe for me to put this voltmeter in series with the resistor, right? And it is safe for me to put the voltmeter in parallel with the resistor. Now, the reason why we can go ahead and put the voltmeter in parallel with the resistor is because it has high resistance. Now, if we know about high resistance, the higher the resistance is the less current that that will be flowing through the component, right? So you want as much as possible to limit the amount of current that is flowing through this voltmeter. So hence the reason why you would have to use or whenever you're designing the voltmeter, you'd have to ensure that it has a high resistance. If you were supposed to use just a voltmeter that does not have a high resistance, then it would take away some of the energy, or some of the current rather, that is required to flow through this resistor, and it would just affect the whole reading, so to speak. Now let's see if we can talk about resistors, right? The magnitude of current that a given EMF produce depends on the resistance of the component. So when we talk about magnitude, we talk about size, right? So if the current value is very high, that can have significant implication on the resistance of the of the uh, of the component, right? And the reason behind this is that the higher the current is, it means that it's more charges that is going to be flowing through the resistor, or through the component. Now, if you have more charges flowing through it, it means that the possibility of having the charges being colliding with other uh what do you call it now, other particles is going to be much higher. And with that, it's going to increase resistance. We'll talk about that a little bit more. Now, we have a particle equation that we use to link these three things: to link voltage, to link current, and to link resistance. That equation is what we call the Ohm's equation, or Ohm's law equation. Now, what this tells us is that it tells us that if V is equal to IR, right? The higher the the total resistance is, good, it's the lower the current will be. Because if we should manipulate our equation so that R becomes the subject, we are left with V upon I. So higher resistance means that less current will flow. And if less current flow, the whatsoever you're measuring, or it will be much difficult for that thing to conduct. So we can say less conduction taking place. Right, less conduction. Because if this is my wire, good, and I have a lot of particles in this wire, so by having this wire and having these particles here, me join these circles is telling us that I'm increasing the resistance. These dots here is increasing the resistance. If I increase the resistance, when current starts to flow, right, the charges that the current brings to this component will be impacted by the material, the makeup of this material. Because we know every material is made up of particles. Now, the more particles we have in the way, it's the more likely, it's more to move something will impact the flow of the charge through the circuit. We see where that resistance is proportional to voltage, which tells us that by increasing the resistance, I would now need to increase the energy per charge, because if you want the thing to conduct, right, it means that the electrons that is flowing will require more energy to do so at a higher resistance. And we expect, with doing all of this, the component will get hot eventually, you know because it is basically forcing its way. More work is being done to allow those charges to pass through. All right. Now, when we talk about resistance, there are different types of resistors, right? We have what we call fixed resistors, and we have a thing what we call variable resistor. As the word suggests, fixed, that's a set value resistor. So you will realize that when you do some experiments or stuff like that, you will come across maybe 1,000 ohms resistor. I should let you know that the unit for resistor is known as ohms, and it looks like this, right? As you can see here, this one is probably a little bit better, right? So that's a symbol, and it was named after who created it and realized that it makes sense and all of that. So the symbol is named after him, ohms. We have what we call a variable resistor, and the variable resistor is one, as its name suggests. It will be able to vary over, versus one that is fixed. All right. So we will come across this some more, the variable resistor. But in the interest of time, let's look at a simple example here that would require for us to calculate the resistance of a so it says that the current in an electric rather immersion heater in a school experiment is 6.3 amps, when the potential difference across it is 12 volts. Calculate the resistance of the heater. Let's see if this resistor has, or if this heater has a high resistance. So the equation that we would use right now is our Ohm's equation, Ohm's law equation, that says R is equal to the potential difference, or is it resistance is equal to the ratio of potential difference to current. So this is what we would start off with. We know the voltage value, or the potential difference across the heater, that is 12 volts. Divide that now by the current, which is 6.3 amps. It's going to be about 1. So the resistance here is going to be very low. So it's going to be 1.93 ohms. This tells us that a heat of this nature, it has a very low resistance. So whenever the current is flowing through this resistor or through this electrical heater, it's going to heat up very quickly, because there's nothing there to impede or to slow. There's not a high resistance, so there's nothing really to slow down the charges when it is flowing through the heater, right? So this is the overall resistance of that heater, and this is just telling us clear and straight that the heater will heat up very quickly, because nothing is resisting the flow of charge. Let's see if we can look at another thing we call electrical heating. Now we expect that whenever current passes through a resistor or any component, it will get hot. This heating effect is called Joule heating. The electrical power produced or dissipate is given by this formula. So we expect that our component is going to get hot over time when we use it, and it's going to lose some amount of heat, right, throughout the process. Now this heat is really a measure of power, right? And in order for us to be able to can find this power that we have generated, right, by just allowing voltage, by just allowing current to flow through a resistor, is given by the formula that says P, which stands for power, is equal to voltage times the current, right? I think we probably would have come across this already too in some aspects of our CSEC course, right? And there are other equations that we can derive to find power just the same. Depending on what information is given to you, you can use either this equation to find the power loss. So this is another, we refer to this equation as power loss equation, right? Power loss. So you might get a question from time to time to say, what is the power loss, in the component. So that is just simply you finding the power, and that is, equal to the voltage times the current. Or we can do some mathematics here. From Ohm's law, we know that voltage is equal to IR, and as of such we can go ahead and make, not make, but we can substitute V in this equation and put IR. So we're left with this. So if I'm subbing V is equal to IR, when I sub it in this equation here, I am left with R times R times, not R times R, I times R times I will end up giving me P is equal to I squared times R. So that's how we get this equation in terms of resistance, right? Then there's another way we can find the power as well. So using our Ohm's law equation again, we know that Ohm's law says R is equal to V upon I. Transposing that to make I become the subject, I is now voltage divided by resistance. So we want to substitute I in our power equation. So if we sub I in P equal I times V, then we are left with P is equal to V over R times V, which leaves us with V squared upon R. So those are the three equations that we can use from time to time to find the power, depending on what is given to you. So if we look at this question, it says, so an electrical, not electrical again, I keep saying electrical, an electric immersion heater used in an experiment has a current value of this, and it says when the potential difference across it is that, it says calculate the power. So this is a very straightforward one. So we'll just go ahead and use P is equal to V times I. We will know V is 12. There should be a volt right here, by the way. So 12 volts times the current. So because it's an electrical heater, we expect that there's going to be quite a large amount of heat that is going to be given off. Well, not a large. I mean, when I do it now, it's not, that's a lie. I thought it was going to be a lot. But this is the amount of heat that will be dissipated across the resistance that is inside of the heater, right? And as a matter of fact, the unit for this is what we call watts, right? It was named after the guy who found out this information, but we could denote watt as saying volt, uh, volt amp, yeah. So in other words, volt is equivalent to, not volt, watts rather is equivalent to volt amp. All right. So if you see volt amp at in anywhere in your text, then it's talking about watts. All right. That's about it. When we talk about the electrical components, I believe we have covered all of what we had slated to cover, right? As regards to knowing what charge refers to as the unit for charge, potential difference, right, and so forth. So in our next lesson, we'll look at some stuff regarding resistors and resistance. So let's gear up for that in our next lesson.